we have a circle with some points on. In fact, 3 points. Now, when we join up these 3 points, we find that the circle is divided into a number of areas. With 3 points, we get 4 areas. Now, what happens if I use a different number of points? Is there some formula that will tell me how many areas I'll get? Can I make a guess, or, as we say in mathematics, formulate a conjecture? Well, let's start again with a different number of points and see if we can get some sort of pattern. Well, here's a circle with just 1 point, and I get 1 area. For 2 points, I have 2 areas. And with 3 points, I get 4 areas. With 4 points, I get 8 areas, and I think I can already see a pattern emerging. I guess with 5 points, yes, that's right, I get 16 areas. Well, I think that the pattern that is beginning to emerge is that we're going up in powers of 2. So, it seems reasonable that our conjecture is, for n points, we're going to get 2 to the n-1 areas. Well, for 6 points, this conjecture will predict that we get 32 areas. So, let's check that. Here are the 6 points. Let's count the areas. Well, it's 31. And no matter where you put the points in the circle, you'll never get more than 31. Well, this is an example of a guess, a conjecture, which actually turns out to be wrong for n equals 6. And it's not the first time that we've had a conjecture which turns out to be wrong. Before the program, we had this conjecture, which holds up to n equals 39 and goes wrong for n equals 40. Again, we used a counterexample to prove the conjecture was false. Well, these were 2 conjectures that were wrong. But what if the conjecture is right? How do we show that it's right? In this program, we're going to give you a method which will enable you to prove conjectures when they are in fact true. So, what we want is a method of proof which enables us to show that a result holds for all the positive integers n. Well, so far we haven't actually had a conjecture which is true. So, the first thing to do is to find a true conjecture. Bob.
The conjectures that we're going to get are concerned with this pile of cannonballs. It's not just any old pile, it's been constructed in a very special way. We started off with a triangular base, and then we stacked them up as efficiently as possible. And that meant that each of the layers is a triangle as well. Well, the top layer's a bit dull because it's just got 1 cannonball in it. The second layer is a triangle of side 2, and it's got 1, 2, 3 in it. So that gives us, in the first 2 layers, 4 cannonballs in total. That illustrates the 2 problems that I'm going to look at. Firstly, how many cannonballs are there in a given layer? Well, in the first one there was 1, and in the second one 3, and in the third one there's 6. But what I'd like is a formula which will tell me how many there are in the nth layer. Now, the second problem is about how many cannonballs there are altogether in the top n layers. For example, in the top 2 layers there are 1 plus 3, which is 4 in total. And in the top 3 layers there would be 1 plus 3 plus 6. That's 10 in total. And again, I'm looking for a general formula involving n. All right, let's look at the first problem. It's perhaps easier to see what's going on if we look at this model. We've stuck the balls together in layers so that we can look at each layer in turn. In the first layer, there's just 1. In the second layer, there are 3, which is made up of a row of length 1 and a row of length 2. Now, the third layer, it's a triangle of side 3 with a row of length 1, a row of length 2, and a row of length 3. So what will the fourth layer look like? Well, it will be a triangle with side 4 and a row of length 1, of 2, of 3, and of 4. And now we can see what's happening. The nth layer will have rows of length 1, 2, 3, and so on, up to n. So the total number of cannonballs in the nth layer will be given by this sum. Well, we've already seen what this sum is. It's n times n plus 1 over 2. And that's true for all positive integers. That's the first of the results that we're going to prove. In fact, you've seen a proof of this result before using Pascal's triangle. But now we're going to use this result to illustrate a new method of proof. It's a proof called mathematical induction. And it's a method of proof which is tailor-made for statements which say something is true for all positive integers n.
The set of positive integers n is going to prove very important in our work. So, what is it? Well, it starts at 1. And for each number in the set, the next one, that is its successor, also belongs to the set. So if 56 is in it, then 57 is in it too. And these two properties define n exactly, the whole of n and nothing else. So you won't find 4.5 in it, and you won't find minus 2 in it either. And we could think of these two statements as actually defining the set of positive integers n. So what's all this got to do with proving statements like 1 plus 2 plus 3 and so on up to n is equal to n times n plus 1 over 2? Well, the method of proof that we're looking at, mathematical induction, involves showing that something holds for all the positive integers. So we start off with a conjecture, and then we think of the set of positive integers s for which the conjecture is true. So s is in fact a subset of n. And what we want to show is that s is in fact the whole of n. So what we need is for s to have the same properties as n. Firstly, 1 belongs to s. That is, it starts at 1. And secondly, if an integer k is in s, then k plus 1 is in s too. In other words, for each number that is in s, the successor is in s. And if we can succeed in showing that s possesses these two properties, then s is in fact equal to n. Well, let's look at this in another way. The contestants here represent the set of positive integers n. And anyone who falls in the pool is falling into the set S. So 1 is an S, and because the successor property holds here, S must be the whole of n. Showing that the set S, for which our conjecture holds, is equal to the whole of n to all the positive integers is the method of proof by mathematical induction. It's a very general method of proof, and it's a very efficient method of proof. Instead of having to check our conjecture for every single one of an infinite number of values of n, and of course it would take you forever to do that, we just have to check these two properties. And then we're guaranteed that it holds for every single positive integer in n. So how do we go about using it?
I'm going to use mathematical induction to prove this formula. Now, in all proofs by mathematical induction, we begin by defining what we mean by the set S. The set S is the set of positive integers for which the result is true. Now, the first step is to show that 1 belongs to S. Well, what does that mean? It means that the statement is true for n equal to 1. Well, when n equals 1, the left-hand side just consists of one term. It's 1. And the right-hand side is 1 times 1 plus 1 divided by 2. So 1 belongs to S means that 1 is equal to 1 times 1 plus 1 over 2. And that's certainly true because both sides are equal to 1. So 1 does belong to S. Now for the second step, we need to show that if k belongs to S, then k plus 1 belongs to S. So as a start, let's see what k belongs to S and k plus 1 belongs to S mean. Now k belongs to S means that the statement is true for n equal to k. So replacing n by k, we see that k belongs to S means that 1 plus 2 and so on up to k is equal to k times k plus 1 over 2. In the same way, replacing n by k plus 1, we see that k plus 1 belongs to S means this. So now we know what k belongs to S and k plus 1 belongs to S mean. Let's get down to verifying step 2. We have to show that if k belongs to S, then k plus 1 belongs to S. Well, if k belongs to S, then this is true. This is what I should call the induction hypothesis. Well, now let's take the left-hand side of the expression for n equals k plus 1. And we've already seen that it's equal to this sum. Now, in fact, it contains just one more term than this. So by the induction hypothesis, we can replace the first part of this sum by this. So the left-hand side is equal to k times k plus 1 over 2 plus the extra term k plus 1. Now, factorizing out k plus 1, we get this, which simplifies to this. And that's equal to the right-hand side of the expression for k plus 1. So the left-hand side is equal to the right-hand side, and the result is true for n equals k plus 1. And therefore, k plus 1 belongs to S. So we've verified the second step, that if k belongs to S, then k plus 1 belongs to S. Now, from these two steps, the principle of mathematical induction tells us that S is equal to n. So the set S for which the statement is true is the set n of positive integers. And that completes the proof that 1 plus 2 plus and so on up to n is equal to n times n plus 1 over 2 for all positive integers n. So that's how the principle of mathematical induction is used to prove that a statement is true for all positive integers n. We look at the set for which the statement is true, and we prove two things: that it starts at 1 and that it has the successor property. Well, our second problem was to find the total number of cannonballs in the top n layers. And we get that by adding together the numbers for each layer. So in the first n layers, we'll have 1 plus 3, and so on, up to the number in the nth layer. And we've just proved that that is n times n plus 1 over 2. Well, I'm going to use mathematical induction again to prove that this sum is equal to n times n plus 1 times n plus 2 over 6 for all positive integers n. As before, I'm going to use s to denote the set of positive integers for which the result's true. Now for step 1, I've got to show that 1 belongs to s. And in this case, 1 belongs to s means that 1 is equal to 1 times 1 plus 1 times 1 plus 2 divided by 6. And this is true because both sides are equal to 1. So I do have that 1 belongs to s. Now for step 2. Replacing n by k tells us that k belongs to s means this. And replacing n by k plus 1 tells us what k plus 1 belongs to s means. Here it is. As in the previous case, the left-hand side contains just one more term than that for n equals k. So if k belongs to s, I can say this. That's the induction hypothesis. Now I look at the left-hand side of the statement for k plus 1. Because of the induction hypothesis, I can replace this first part of the sum by this. So this left-hand side is equal to this plus the last term, k plus 1 times k plus 2 over 2. Now I factorize out the two terms, k plus 1 and k plus 2, to get this, which simplifies to this, which is equal to k plus 1 times k plus 2 times k plus 3 over 6, which is equal to the right-hand side of the statement for n equals k plus 1. And therefore, I do know that k plus 1 belongs to s. So, if k belongs to s, then k plus 1 belongs to s. Now I've checked steps 1 and 2. So by mathematical induction, I can conclude that s is equal to n. So this statement is true for all positive integers. So that's how we use mathematical induction to prove the two conjectures about this pile of cannonballs.
These two results were about sums, and they were done in the same sort of way. There was one extra term to add on. But sums aren't the only things that you can prove by mathematical induction. It's about statements which are true for all the positive integers n. And here's one we looked at before the program. It's proving that this expression is divisible by 8 for all positive integers n. So we've two things to prove about the set S for which the statement is true. One, that the number 1 belongs to S, so that if I substitute 1 in this expression, I get 1 squared minus 1, which is 0, and 0 is certainly divisible by 8. It's 8 times 0, so this works. Now what about the second property? If k is an S, then k plus 1 is an S. Well, what does k substituted here give me? It gives me 2k minus 1 all squared minus 1, and that in S means it's divisible by 8, so it's 8 times some integer a. Well, I can simplify that, and I get 4k squared minus 4k is equal to 8 times a. Now, what does k plus 1 in S mean? Well, I get this rather nasty expression here, but again that simplifies, and I can write this as 4k squared plus 4k. And I have to show that that is equal to 8 times an integer. I've got to prove that using the result I got for k. Well, I can actually rewrite that using this result. That's 4k squared minus 4k plus 8k. I haven't done anything to that. And now we see that this expression I've got here is just what I got for k. In other words, that is a multiple of 8 times an integer. And so, by gathering these two terms together, I have that the expression for k plus 1 is 8 times the integer a plus k. So in fact, I have proved the second property. If k is an s, then k plus 1 is also an s. I've proved both properties for s, so my conclusion is that the expression that I started with is divisible by 8 for all the positive integers n. So we've seen how useful and economic the principle of mathematical induction is. It enables us to prove conjectures for all the positive integers using only two properties. But what happens if either of these two conditions fails to hold? What if the first condition doesn't hold? That is, 1 isn't an s. Then we just can't get started. Our conjecture falls at the very first hurdle. But what if the second condition fails? If k plus 1 doesn't automatically follow k, then there's a break somewhere in the chain, and s can't be the whole of n. But what would happen if we didn't have 1 or 2, but we start at 3, and we do have the successor property? Well, this time s is all the positive integers starting at 3 onwards. So if this condition doesn't hold, but instead we start at 3, and we've still got the successor property, well, we can still use mathematical induction. But now we'll use it to prove our conjecture is true for all positive integers starting at 3. So let's finish with an example where we can't start at 1. We're going to look at the sum of the interior angles of an n-sided figure. Now, you can't have a one-sided figure, and I suppose you can't have a two-sided figure, so let's start with a triangle. When the number of sides is 3, then the sum of the angles is pi. With 4 sides, we've got an extra triangle, so the angle sum is 2 pi. When the number of sides is 5, again, there's an extra triangle. So the sum of the angles is the result for 4, that is 2 pi, plus pi for the extra triangle. In other words, 3 pi. And it's the same for 6 sides. It's a pentagon with an extra triangle. So the angle sum is 3 pi for the pentagon with an extra pi. 4 pi altogether. And if you look at the pattern in the table, for an n-sided polygon, it looks as if the angle sum will be n minus 2 times pi. And how do we prove this conjecture? By mathematical induction.